Okay, so we've been talking about the different kinds of particles, elements, compounds, mixtures, and this week, another way of classifying phases gas, liquid, and solid. Now, all particles, regardless of their state of matter, are in motion, and how they move depends on a lot to the extent what phase. Right? Solids vibrate in a fixed position, as you can see over here. Right? It's very small, but they are moving. Liquids slide and flow past one another, and the gases are very far apart, much faster, and move in constant straight line motion. All these particles also have space between them. The amount of space depends on the phase of matter. Right? There's very little space, but there is still some between solid particles. There's a little more space between liquids, and a lot of space between gas particles. Also, all particles have intermolecular forces of attraction between them. In a solid, those forces of attraction are very strong, and they pull each other towards each other and keeps them very tightly packed. Liquids are a little more moderately held together, and gases have very weak intermolecular forces, and they're very far apart because of that. Intermolecular forces also depends upon bonding, which we'll learn about in January. Let's look at solids. Again, solids at the particle level are vibrating and moving, right? The floor underneath your feet, those particles are moving, but the movements are so small we can't perceive them. Solids cannot be compressed, not true solids. And they're very organized. Usually we hear the term crystal or crystalline. And again, they vibrate in a fixed position. They have low entropy because they are so organized in those crystal shapes, those geometric shapes. And they have strong intermolecular forces. A way to remember it, solid S, solid, solid, strong S. Right, so they both start with S. Solids are strong forces. And most of the elements on the periodic table are solids at room temperature or standard temperature. Yeah, we can take a look here at some of these crystal shapes that you see for solids. We have salt, sugar. Under the microscope, this is what they look like. They have that crystalline shape. There are some other ones that are very beautiful. And hopefully this year you'll get a chance to make one or two of your own crystal solids. Even a lot of metals have this sort of very crystalline geometric shape, as well as all these beautiful minerals that maybe you've studied our science. Again, notice how geometric their shapes are. Okay, we'll continue on. Liquids. Liquids, you can see, are moving and sliding past one another. There's a little more space between them. They're also still non compressible because they are still pretty close to each other. They're a little more disorganized than solids. They can flow. Their entropy is, higher than a solid, but less so than a gas, in between, medium. And again, they can evaporate, right? Okay. And lastly, gases. Gases are the most complex form of our phases. And we have a whole theory sort of regarding them, the kinetic molecular theory, or KMT. Gases spread out, they're highly compressible. They have a lot of space between them, so you can compress them. You can push down on that balloon, or think about all the air that's inside the marshmallow. You can compress that air and squish the marshmallow. Very disorganized. Gases can actually flow and pour. They have high entropy, they're very disorganized, and they have weakened molecular forces. That's how they're able to be so far apart. They don't attract each other very well. Okay, so again, some things we've talked about. Right? Their volume is insignificant because there's so much space between them, right? That the little particle itself is insignificant compared to the space they take up. They're moving in random, constant straight line motion, and they're bouncing into the walls of their container. They are compressible, they can be squished. Okay, we can see here in this picture, you can decrease, you can push down on that plunger of a syringe or a tire pump. And that's how our car works, right? The pistons in our car. We have the gases being pumped in and out, creating that energy. Ideal gases versus real gases in the real world. Right? So, how are they basically the same thing? Well, the temperatures must be high because gases want to move very quickly, and at high temperatures, things move quickly. And the pressure must be low, right? Nothing should be pressing down and compressing them. They should be allowed to spread out. That's what gases want to do ideally. So, ideal gases occur at high temperatures and low pressures. What is pressure? Pressure is the result of collisions between particles and the walls of their container. You can see here, there's a lot more space. They're colliding with their container less often, lower pressure. But if there's less space to maneuver in, they're hitting their sides of their container more frequently, higher pressure. We have pressure pressing down on us all the time, atmospheric pressure. The particles in the air, the atmosphere, are always colliding with your head and pushing down on you. What happens when pressure inside a container is decreased, but the outside atmospheric pressure remains the same? What would happen? Let's take a look here. Inside this carrier, this right big container here, they were decreasing the pressure inside, but the atmospheric pressure pushing down on it didn't change, and eventually was able to crush or overcome whatever little pressure was left inside. It's called the can crush.